For data 1, we will input the memory scores for the mole condition. 8, 7, 8, 6, 9, 12, 7, and 8. This is a collection of everything that we have calculated so far in the process of calculating the test statistic. And this is now our table. For the APA format guide, a one-way analysis of variance ANOVA was conducted to assess the impact of different surroundings on memory scores. The results revealed a statistically significant difference among the three groups, with an F-statistic that is equal to 4.2361 and a p-value that is less than the significance level alpha of 0.05. In this video, we will be performing a one-way analysis of variance, or ANOVA. The question goes, researchers aim to investigate whether different surroundings have an impact on the ability to remember a list of words. To explore this, subjects are randomly assigned to three distinct conditions: a shopping mall setting, a driving in a car setting, and an outdoor setting. The memory scores for each condition are as follows. Perform a one-way analysis of variance at a significance level of alpha is equal to 0.05 to examine whether the surrounding environment significantly influences the ability to remember a list of words. If the result is significant, proceed with post-hoc testing using Fisher's least significant difference to identify specific pairwise differences between the settings. We start with opening the app, and then we click the menu over here and search for one-way ANOVA. We click this calculator. Here, we will be presented with boxes where we input the given datasets. We will be able to input up to 10 sample data. For data 1, we will input the memory scores for the mole condition. 8, 7, 8, 6, 9, 12, 7, and 8. Now for data 2, for driving condition, we have 8, 7, 5, 8, 10, 10, 12, and 8. And lastly, for data 3, the outdoor condition, we have 15, 10, 12, 9, 14, 10, 8, and 10. And then for the significance level alpha, we are also given the value of 0.05. Now that we have already filled up the required values, we are now ready to perform the test. We click the Perform Test button over here and watch and add to unlock the solution. Here, we will be presented with a brief description of what a one-way analysis of variance is, followed by a summary of the given datasets. For step 1, we formulate the hypothesis. The null hypothesis HO states that all group means are equal. In symbols, this can be written as, since we are comparing three samples. On the other hand, the alternative hypothesis H1 states that at least one group mean is significantly different from the others. For step 2, we calculate the degrees of freedom. And as stated here, there are three values that we need to calculate in this step. These are the degrees of freedom for treatment, or the degrees of freedom between groups, the degrees of freedom for error, or within groups, and the degrees of freedom total. To calculate the degrees of freedom treatment, we have to count the number of samples we are working with, k, and then subtract 1 from it. Since we are working with 3 samples, it follows that the degrees of freedom for treatment is k minus 1, 3 minus 1 is equal to 2. To calculate the degrees of freedom for error, or within groups, we have to count the total number of individual data points in all of the samples and subtract k from it. Now solving for the total sample size, we have the sample size for sample 1 plus the sample size for sample 2 plus the sample size for sample 3. Since there are 8 data points in each of the samples, 8 plus 8 plus 8 is equal to 24. And that is the total sample size. Now to calculate for the degrees of freedom for error, we subtract k from n. So 24 minus 3 will be equal to 21. Now lastly, for the degrees of freedom total, we have to count the total number of individual data points in all of the samples and subtract 1 from it. Okay, so as a result, since we have 24 as total sample size minus 1, that gives us 23. Now it's important to check that the sum of DF treatment and DF error must be equal to DF total. So in this case, 2 plus 21 must be equal to 23. Now for step 3, we now determine the critical value. In this case, we will be using the F tables in order to determine the critical value. Now we need 3 values before we proceed to the F table. And these are the significance level alpha, which was given in the problem as 0.05, the DF treatment, which is equal to 2, and the DF error, which is equal to 21 that we have solved a while ago. So now we proceed to the F table. Now we click this link over here. In this website, we'll try to look for the appropriate F table for our test. So in this case, we have F table for alpha equal to 0.10. Since our alpha is 0.05, so we look elsewhere. So here we have F table for alpha equal to 0.05. So this is the table that we are concerned about. We look for DF treatment in this row. So here, df1 is equal to 1, df1 is equal to 2. So in this case, this is the column that we are concerned about. So the next one is df2. This is our df error. Okay, so in this column, we try to look for the value of 21. We have df equal to 21 in this particular row, and the intersection between this location and this location will be the critical F value, which is equal to 3.4668. We see that the critical F value is 3.4668. Now for step 4, we formulate the decision rule. The F distribution commonly used in ANOVA test is right skewed. Therefore, when conducting an ANOVA test, it is typically structured as a right-tailed test to determine whether there is a significant difference among group means. To formulate the decision rule, we will use the critical value approach, which means we compare the calculated F statistic with the critical F value. As a result, the decision rule is to reject the null hypothesis if F is greater than 3.4668. Otherwise, fail to reject the null hypothesis. As we dive into step 5, we're about to embark on the journey of calculating the test statistic. While the process may seem lengthy, remember that nothing is too challenging when we break it down step by step. First, we will need to calculate each of the sample means as shown here. Since there are 3 sample datasets, it is expected that we will have 3 sample means: 8.125, 8.5, and 11. Next, we will calculate the grand mean. In other words, we will take the average of the 24 individual data points coming from the 3 samples as shown here. Our grand mean is equal to 9.2083333. Next, we have to calculate the sum of squares for treatment, sum of squares for error, and sum of squares total. For the SSR, we have the following formula. So we multiply the total number of individual data points n to the sum of the squared differences between each group mean and the grand mean. In symbols, we have, so this is x bar 1 minus the grand mean squared. This is x bar 2 minus the grand mean squared plus x bar 3 minus the grand mean squared. The square differences is multiplied to the total sample size of 24, giving us an SSR of 39.083333. For the sum of squares for error, we take the sum of the square differences between each individual data point and their corresponding group means. In other words, each of the corresponding sample mean will be subtracted from the individual data points within that sample, and the sum of the square differences will be that sample's contribution to the sum of squares for error. We then add the contributions of each sample to have the sum of squares for error, SSE. For SST, we take the sum of SSR and SSE that we have calculated earlier, and this is our SST. Next, we have to calculate the mean squared between groups and the mean squared error or within groups, the MSB and MSE. Basically, we divide the SSR with the DF treatment and we get the following result. And for MSE, we divide the sum of squares for error by the degrees of freedom for error and we get the following result. And lastly, to calculate the test statistic F, we divide MSB by MSE and we get the following result.